Hello. So welcome to the last problem in the 2019 midterm live solve for Stat 111 Stat 111. This is, yeah, pretty fun normal distribution problem. And as usual, I recommend you guys take a look at the problem yourself and give it a try before you come back. And then you can watch this video with emotional attachment to the problem. I'll go ahead and get started. So first, bacteria levels in a certain pond are measured each morning. If the measurement is above a certain threshold C, swimming is deemed to be dangerous and the pond is closed for the day. Let Yj be the measured bacteria level on the jth day. So we have this like measurement level. And suppose that these are IID with distribution this. Wait, this seems like, is this the correct problem? Oh, yes, it is. Okay. I was looking through a different problem earlier. So where mu is unknown and sigma is known. And this doesn't change over time, blah, blah, blah. We observe y1 to yn, where as yn plus 1 will be tomorrow's measurement. So let theta equal the probability that yn, so tomorrow's measurement, will be greater than c. And your answers in this problem can be in terms, so this seems like a hint. Okay, so first find the MLE of theta. So we want to find the MLE of theta, which is theta equals probability yn plus 1 greater than c. I'm guessing we want to use invariance on this question. So let's figure out exactly what theta is. So this is going to equal 1 minus probability yn plus 1 less than or equal to c, which is something we can do maybe a CDF kind of thing on. This is like, let's standardize. So yn plus 1 minus, it should be minus mu over sigma is less than or equal to c minus mu over sigma. And now this is going to be a standard normal. So this is going to be 1 minus big phi c minus mu over sigma. So that's pretty useful. That gives you a relationship between mu of the normal and theta. So we know the MLE of mu. So by invariance, we can get the MLE of theta. So why do we know the MLE of mu? MLE of mu, which is the mean parameter. We've seen this a bunch of times. This is going to end up being y bar, the sample mean. So now we have by invariance of the MLE, we have theta hat equals 1 minus big phi of c minus y hat, y bar over sigma. And let's make sure all of, so c is a constant, sigma is a constant, and y bar is our data. So that makes sense for the form of an estimator. So here's our MLE. Next is find an unbiased estimator for theta. So theta is the probability, like this probability, right? And we want it such that the expectation is that true probability. So here's one of them, theta hat, and this is going to be like unbiased version. Let's just take, this is like the absolute dumbest thing you can do, but it's an estimator because it's a function of the data. If I give you data, you can spit out this estimator, or I guess the estimate. And it's unbiased because it's going to genuinely equal theta, but that's just taking the first data point, or really any data point, like the nth data point works too, because it's all IID, and checking to see if it's C. And this is going to end up having like expectation, like probability y1 greater than c. Like the expectation of this is just going to be like theta itself. So this is, that's by like the fundamental bridge. Yeah. Oh, wait, my bad. Hang on. This should be indicators. Indicator of that. Therefore, the now by the fundamental bridge, we have probability yi or y1 greater than c, which is equal to theta. That makes a lot more sense. So here's our dumb estimator that is unbiased. generally you don't really have to come up with like intelligent estimators if it's just asking you for an example, unless it asks you to make it intelligent. But yeah, so it asks whether your estimator would be unbiased if the model was misspecified. So we still have all of the YJs being like IID. Oh, we still have all the YJs being identically distributed, but they don't have to be independent and they don't have to be normal. So in this case, like it doesn't, we're only using one data point. So it's just going to be like the independence doesn't affect it. So that's fine. And normality also doesn't affect it because no matter what the fundamental bridge is going to hold, and as long as this like tomorrow measurement, this tomorrow measurement is just going to be like it's going to have the same distribution, whether or not that's normal as Y1. So this is all fine. This is just dependent on marginals. So still fine with misspecification. Cool. So use Rao-Blackwell to find an unbiased estimator that is better than the one from V. So great. Okay, so let's use let's like Rao-Blackwellize our B, which is unbiased. So we're just going to improve the variance. And right now it doesn't look like it's like in terms of any like sufficient statistics, which is when the Rao-Blackwellization won't do anything to the variance because of conditional expectation arguments. So using properties of the multivariate normal, blah, 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 it can be shown that. So maybe that's useful. So we're going to go Rao-Blackwell. And this is going to be expectation of our unbiased data hat given a sufficient statistic. So our sufficient statistic in this case is going to be Y bar. So because like the normal with known like sigma squared is like an NEF, then we know that Y bar is a sufficient statistic. And you might derive inspiration from this comment here. Okay, so that's fun. This is equal to, if you recall, this is expectation of the indicator yi greater than c given y bar, and then this is going to be probability of yi greater than c given y bar. So maybe that's going to be useful. So let's use the hint now, because this will give us this distribution that we're interested in, the conditional distribution. That's for the IID standard normal. So we're going to have to inflate it a little bit with multivariate normal. So right now we have, we're going to have like, let's call, so Y1 is going to be equal to, so Y1 is distributed as mu sigma squared. So this is going to be equal to mu plus sigma times z with z standard normal. I guess like standard normal, so normal 0, 1. So this time we're given like our y bar is going to be just, let's see how to explain this. Yeah, so just like kind of pattern matching here. We have this is normal around z bar and 1 minus 1 over n. Then we have that y1 given y bar. It's also going to be around y bar, but now our this is going to get inflated a little bit, and it's going to get inflated by this. So sigma squared 1 minus n is what's going to end up happening. Great. And you don't need to show any of that. You can just go from here to here. And you can kind of like, to get this, you can think of like, this is just, we have n times mu, or I guess mu plus sigma squared over n like z bar instead is going to equal y bar, not sigma squared. Just sigma over n, I think. Un sum of zn. Yes. Okay. Cool. So now we have this like this distribution here, which is going to be useful, and we're going to use that for here. So this is going to equal the 1 minus probability y1 less than c given this y bar thing. And this y1 given y bar, this is now, we know the distribution of it. It's like normal with that stuff. So this is going to equal phi of, let's standardize. So y1 minus, it's going to be c, because I'm taking this side, minus y bar, the mean, over the standard deviation, so sigma, and then 1 minus 1 over n, and then minus 1. So this is going to be our Rao-Blackwellized estimator. And to check, we know that c is a constant, we know n is a constant, y bar is a function of the data. And yeah, so that's our better data. And that is clearly different from this like indicator up here. Just by, looking at it, it's completely, it's part of, or I guess it's constructed by like y bar, which is completely different data. Cool. Okay, so next, assume now there are two different technicians who measure the bacteria levels. One is very precise and the other is very careless. Measurements are made by technician 1 with normal mu sigma squared 1. Other one is normal mu sigma squared 2. And we have that like, this guy is a lot smaller. So what we're looking at is like, we have like one like usual normal and then one's like a really bad normal. Maybe something like that. Oh, that's not symmetric at all. Let's see. I don't even think maybe I should make this the like better normal. So we have, so this is going to be like technician 1. This is going to be technician 2. It is randomly decided which technician will make the measurement that day. With equal probabilities, assume independent across days. For this part, we assume we get to observe the measurements, and we know which technician made it. So first, we want to find a method of moments estimator for mu, and then explain intuitively whether method of moments or MLE is a better approach, or whether they're the same. So this is a normal mixture model. So it is going to look, if you wanted to write it out in like the notation that people like to use for these things, it's like 1/2 normal mu sigma 1 squared plus 1/2 normal mu sigma 2 squared. And that doesn't mean you're like summing up the normals. It means with probability 1/2, it's going to come from the first one, and with probability 1/2, it comes from the second one. So that's pretty fun. And we also know, like, I guess we have like the coin flips that decide whether it's going to be 1 or 2. So maybe in like this problem, you're going to have to think about like a diabolical, there's one very wide distribution and one like maybe very narrow distribution is my guess. So method of moments estimator for mu. So mu is the like, I guess, okay, so we have expectation of the y, the data. So this is the theoretical mean, and that's going to be just mu no matter what, because like this has like, no matter what, this has like it's either going to come from this or this, but both of them have the same mean. So we're going to end up having the same theoretical mean as the original two distributions. So we have mu, and then we're going to want to set the sample mean to it. So we have y bar equals mu hat mom, and then that's it. Like we don't have to do anything else. So we have, I guess I'll write it the way a normal person would. So here's our mom estimator. It is just taking the sample mean of everything. So here's the intuition for whether method of moments or MLE is better. You don't have to compute it. It's actually it's a little gross. So intuitively, like the mom estimator just doesn't really, like they might as well have come from the same distribution. And even if all of them, like, I think intuitively you would think maybe better to just look at the like technician 1 measurements. Because if we have for an extreme example, like maybe sigma 1 is equal to like 0.001 is sigma 2 is equal to like 100, right? You might be more inclined to look at sigma 1 measurements than sigma 2 measurements, just because they're just going to be very tightly packed around what we anticipate our true mean to be. So the mom estimator kind of disregards that completely. We're going to look at all of our data points and we're going to weight everything equally. The MLE is going to look somewhat of a weighted mean, where we give a little more credit to the technician 1 measurements than the technician 2 measurements. So intuitively, want to use knowledge of sigmas and who did each measurement. So MLE is better intuitively. Okay, so the last part says continue as in D, except now suppose we do not find out which technician made each measurement. So we don't know who did what. We can only observe the measurements, and then find a mom estimator. Well, we still, like, every point, or I guess every random draw, whether it came from technician 1 or technician 2, is going to have mean mu. So in the end, this is again going to have the same mean mu. So we have expectation of y1 equals mu. So we get a sample, we set our sample mean equal to mu to solve for the mom estimator, which is just going to be the same thing. So we have the same mom estimator. And now we're going to explain intuitively which one is better. So in this case, it's like, you can't really say exactly this thing. You can't like weight it exactly, throw out some things, because some of them are going to come from technician 1, some of them technician 2. Maybe if it was like really extreme, like you could guess, but you don't actually know which technician measured each one. Here, so it says which one is a better approach to this problem, or whether they're the same. So in this case, the MLE is going to take into account the sigma squareds because we know the sigma squares. So that's important to know. Know sigma squared 1 and sigma squared 2. And the MLE is going to incorporate some likelihood of a mixture model, which is going to incorporate these guys. And then in the end, it's going to be like pretty disgusting, but we will get something that is different because we have a lot more knowledge about these than in the method of moments, which just throws out everything that we know about sigma and just considers the sample mean. So this is all very intuitive, hand wavy. Well, maybe not hand wavy, but very intuitive. I didn't want to compute anything because it's not very fun to compute. And we wouldn't expect you to compute it here if it asks you intuitively. What are some other things that we like about the MLE just in general over the mom? So the MLE is consistent, which is great. We have the MLE uses all model info, whereas mom does only looks at the sample mean. And the MLE like has a nice asymptotic distribution. And it reaches Cramer-Rao lower bound asymptotically. So MLE in general, like it, for this example too, is usually a little nicer than a mom with respect to like its mathematical properties. Yeah, kind of a philosophical question to end this midterm, but that's the end of this problem. I hope you guys enjoyed this. I plan to make another one for the final probably. And as for study tips, I would say pay attention to like all of these midterms, like the practice midterms. I find those really useful. The additional practice problems, since we revamped this course like 2 years ago in 2019, those are really good to look at. And I think the homeworks are also pretty important to understand what's going on. Of course, you'll have access to your notes, but back in the day, we would like make a like finite length cheat sheet, and I always found that a really good way to study. So maybe you could do that just for fun, or not. But yeah, good luck on the midterm, and thanks for watching.